Let's see what I have. I'm going to take the photonic crystal lecture out of a paper by Bush and John. Okay, Kurt Bush. I will send you this paper in an email. It's Sati. John. And this was published in 1998. Physics Review E, Volume 58, Number 3, 1998. Okay, on photonic band gap formation in certain self-organizing systems. Okay, and in this paper they solve Maxwell's equations for a periodic structure. I just go through some of the equations that they have. And how they compute band structures for photonic crystals. So if we have a Maxwell's equation corresponding to a potential that is periodic, we can do the 2D case. 2D case, we can think of that for easy polarization. Then Maxwell's equations can be converted into vector wave equations that look something like this. E of R is actually what I call my rho. This R here consists of only X and Y variation in this paper. And then E is usually what we call EZ. Okay, the electric field polarized in the Z direction. So we have to solve an equation something like this for photonic crystal in 2D EZ polarization. Okay. And then because EP R plus RL will be equal to EP R. If this is a periodic photonic crystal, the permittivity will have this property. Okay? Because it has this property, you can Fourier expand the 1 over epsilon P of R in terms of a generalized Fourier series. Eta T e to the I G dot R. This means that we sum over all L1, L2, and L3 in this generalized Fourier series. Okay, and this is like Fourier series transform of this function. Okay. So how do we convert this into an equation? And I guess the idea here is that if I make my solution to be a block blockade wave, this essentially can be converted into a matrix equation that consists of an eigenvalue problem of the kind of A dot X must be equal to, or maybe if I just write it this way, X is to the 0. So this is the matrix eigenvalue problem. Okay. The key is to convert this into a matrix system and solve. And then solve for all the possible eigenvalues. And those eigenvalues will be the band structure calculation, kind of. Let's see how we do that. So let's assume that this is the block blockade wave to begin with. So as I said before, the block blockade wave assumes that there's an incident wave in the background, which I said before, there's an incident wave plus a scattered wave. So the block blockade wave in general is a periodic wave of this type, and in this paper, which I will mail to you, we write this block blockade wave in this manner. E to the I K plus E dot R. So they factor this e to the ikr into this periodic function. And that periodic function has already been expanded in terms of a generalized Fourier series. Okay, so this is a block or gateway that satisfies this problem. And then you plug that in there, and it's quite easy to show that the first form, the transverse Laplacian operating on this thing here, would operate on this part over here, and since it operates on it twice, it will give you, if you take the order of differentiation and summation and exchange them, you will have just this left. And then you will have k plus g dot with k plus g dot with e to the I k plus g dot r, right? You just have that if you just work out this part. And then this part is a little bit tricky. It is a multiplication in the coordinate space. So it will correspond to a convolution in the Fourier space. And then you take it back to the coordinate space. Okay? It turns out that the convolution theorem still holds true with this generalized Fourier series. You can prove that as homework very easily. Multiplication in coordinate space corresponds to a convolution in the Fourier space. So what we need to do then is that if we multiply this by this, we will take this Fourier coefficient and then convolve with this in the Fourier space and then take it back again. Okay, the effect of this is rather simple, but if you work it out carefully,